You're standing in the dead center of the biggest continent that's ever existed on Earth. And I mean ever. We're talking about Pangaea here, this absolutely massive supercontinent that was basically every piece of land on the planet just smooshed together into one gigantic landmass. And you're standing right in the middle of it, thousands upon thousands of miles from the nearest ocean. It's dry, like crazy dry. The kind of dry where you look around and there's just nothing but arid desert stretching in every direction as far as you can see. If you're using these to fall asleep, that's literally why I make them. So subscribe maybe, and tell me, where are you and what time? I check comments and it's like Berlin at breakfast, Boston at bedtime, all at once. But then something happens. You feel it on your skin first, this weird change in the air, the temperature shifts, and then you see it, these dark clouds rolling in from absolutely nowhere. And the rain starts to fall. Just a drizzle at first, then harder, then it's really coming down. You're probably thinking, okay, cool, a rainstorm, that's nice for this desert. Except here's the thing that's going to blow your mind. This rain, it doesn't stop. Not after an hour, not after a day, not after a week. This rain keeps falling for over 1 million years. Yeah, you heard that right. 1 million years of continuous rain. I know what you're thinking because I had the same reaction when I first learned about this. How is that even possible? Like, how does it rain for 1 million years straight? What kind of event could possibly cause that? And more importantly, what does that do to a planet? Because spoiler alert, it completely changed everything. This wasn't just some weather pattern. This was the kind of event that literally terraformed the entire Earth and gave us the dinosaurs, basically. Without this million-year rainstorm, the world as we know it wouldn't exist. So let me back up a bit and set the scene properly, because this story is absolutely wild, and it all starts about 230 million years ago during something called the Carnian pluvial episode. Scientists have this habit of giving really boring names to the most incredible events in Earth's history, don't they? The Carnian pluvial episode. Sounds like something you'd fall asleep reading about in a textbook, but trust me, this thing was anything but boring. Picture Pangaea again. This supercontinent was so massive that it made every continent we have today look tiny in comparison. If you took North America, South America, Africa, Europe, Asia, Australia, Antarctica, and just mashed them all together, you'd have Pangaea. The thing was enormous, and because it was so huge, the interior was this vast desert wasteland. See, when you're that far from any ocean, you don't get much moisture coming in. The coastal areas might have been okay, but the middle, forget about it. Bone dry, the kind of environment where only the toughest species could survive. During this super dry period, which lasted for millions of years, evolution was doing its thing in some really interesting ways. You had these creatures popping up that were specifically adapted to survive with very little water. Dragonflies showed up around this time, giant millipedes, spiders. These were the early pioneers, the ones who figured out how to make it work in this harsh environment. And there was another group that was starting to emerge too, one that's going to become really important to our story. They're called archosaurs. Now, you might not know that name off the top of your head, but you definitely know what this group includes. Crocodiles are archosaurs. Birds, believe it or not, are archosaurs. And yeah, eventually dinosaurs would come from this group too. But we're getting ahead of ourselves here because at this point in the story, dinosaurs were basically nobody. They were around, sure, but they were small, not particularly impressive, definitely not the dominant species. They were just kind of hanging out, trying to survive like everything else. The real danger during this time wasn't coming from asteroids or comets or anything Hollywood likes to show us. No, the real threat was brewing beneath everyone's feet, or more accurately, beneath the Earth's crust. Because here's something that's kind of terrifying when you really think about it. The crust we all live on, this thin layer of rock that holds literally everything we know and love, it's vanishingly thin. Like, if you represented the entire Earth as the complete Lord of the Rings trilogy, all 3 massive books, the crust where all known life exists would be confined to a single page. 1 page. That's it. Everything else is just hot, molten chaos underneath. And beneath that thin crust, you've got these massive plumes of superheated material rising up from the Earth's core. Think of them like underwater mushroom clouds, these huge columns of molten rock pushing upward, spreading out as they rise, pressing against the underside of the crust. Eventually, these plumes find weak spots and they punch through. They don't care about tectonic plate boundaries or fault lines or any of that. They just burst through wherever they happen to meet the surface. And when they do, you get what's called a flood basalt eruption. These aren't your typical volcanoes. We're not talking about a mountain that blows its top and causes some regional devastation. Flood basalt eruptions are on a completely different scale. They can release magma continuously for over 1 million years. 1 million years of lava just pouring out onto the surface. The results are these enormous formations called large igneous provinces, and they're scattered all over the world today. You've got the Siberian traps in northern Russia, the Deccan traps in western India, and the one that's going to be our main character in this story, the Wrangelian Large Igneous Province, which spread across what's now Canada and Alaska. These flood basalt eruptions are linked to mass extinction events throughout Earth's history. Most of the time, when one of these things goes off, it's absolutely catastrophic for life on the planet. The most famous example is probably the Great Dying, the Permian-Triassic extinction event, where over 90% of all species on Earth just got wiped out. Ocean temperatures rose to 40 degrees Celsius. 40 degrees. That's like bath water. Imagine the entire ocean turning into a hot tub. Nothing could survive that. It was the closest life on Earth has ever come to being completely extinguished. So when we see evidence of a massive flood basalt eruption in the geological record, scientists typically expect to find a corresponding mass extinction event. The 2 things usually go hand in hand. Huge eruption equals lots of death. It's been that way for most of Earth's history. But here's where our story gets really interesting. The Wrangelian eruption, the one that kicked off our million-year rainstorm, it did cause an extinction event. About 30% of ocean species got wiped out during what's called the Carnian pluvial episode. But here's the weird part. The overall biodiversity on Earth didn't really decrease. In fact, in some ways, it increased. How does that make any sense? How do you have an extinction event that doesn't really decrease biodiversity? Well, turns out the Wrangelian eruption was just the right size. Not too big, not too small, but just big enough to shake things up without completely destroying everything. Think of it less like an extinction event and more like a massive reshuffling of the deck. Yeah, a bunch of species died out, species that were adapted to that dry desert environment. But at the same time, a whole bunch of new species emerged, ones that were way better suited to the new, wetter world that was being created. See, what happened was this. The Wrangelian eruption started pumping massive amounts of carbon dioxide into the atmosphere. But it didn't stop there. The magma was erupting in an area that had huge deposits of coal just sitting underground. Untapped, virgin coal beds that had been accumulating for millions of years. Now, I'm sure you remember the fire triangle from school, right? You need three things for fire: fuel, heat, and oxygen. Well, when you introduce 1600 degrees Celsius magma to the bottom of a coal bed, you've definitely got the heat and the oxygen, and coal is literally compressed plant matter. It's pure fuel. So these coal beds started burning, just absolutely going up in flames on a massive scale. And when coal burns, it releases huge amounts of carbon dioxide and other greenhouse gases, along with tons of particulates that help form clouds. All of this got pumped into the atmosphere on top of what the volcanic eruption itself was already releasing. The alien observers in our story, these hypothetical time travelers watching this whole thing unfold, their instruments detected atmospheric carbon dioxide levels exceeding 1,000 parts per million. That's 2.5 times higher than what we have today, even with all our industrial pollution. And here's where it gets really interesting, because this is essentially the same mechanism that's driving climate change today. When you pump greenhouse gases into the atmosphere, they trap more of the sun's energy. That energy has to go somewhere. It can't just disappear. So where does it go? It goes into Earth's systems, and the system that's best equipped to absorb and distribute that energy is the water cycle. The water cycle becomes supercharged. Think about how the water cycle normally works. The sun heats up the land and the oceans, water evaporates and rises into the atmosphere as vapor. It gets carried by winds and air currents, and eventually it condenses and falls back down as rain, which flows back to the ocean to start the whole process over again. Now imagine turning up the heat on that cycle. More energy means more evaporation. More evaporation means more water in the atmosphere. More water in the atmosphere means more clouds. More clouds means more rain. And if you keep adding energy to this system for long enough, the rain just keeps coming and coming and coming. That's exactly what happened during the Carnian pluvial episode. The Wrangelian eruption kept pumping out carbon dioxide, the coal kept burning, the greenhouse gases kept trapping solar energy, and the water cycle kept accelerating. Temperatures rose by 3 to 4 degrees Celsius globally. That might not sound like much, but it's enough to completely transform global weather patterns. The amount of water in the atmosphere skyrocketed. Clouds that normally would have dumped their rain along the coast started making it further and further inland. Remember, Pangaea's interior had been a desert for millions of years because moisture from the ocean never made it that far in. But now, with all this extra energy in the system, those clouds were travelling deeper into the continent than ever before. Rain started falling in places that hadn't seen significant rainfall in ages. And it didn't just rain for a day or a week or a month. It rained for over 1 million years, with multiple distinct periods of intense downpour separated by slightly less intense periods. Scientists have identified 4 major pulses of rain during this time, each one carving its mark into the geological record. Now imagine you're a species that evolved to thrive in a hot, dry desert environment. You've spent millions of years adapting to conserve water, to survive in arid conditions, to compete with other desert-adapted species. Your entire evolutionary strategy is built around scarcity of water, and then suddenly, water is everywhere. It's falling from the sky constantly. Your desert home is turning into a swamp. The plants you eat are dying off and being replaced by species you've never seen before. The temperature is rising. The pH of the soil is changing because the rain isn't just water, it's carrying acids. See, the Wrangelian eruption wasn't just releasing carbon dioxide, it was also releasing hydrogen sulfide, that lovely gas that smells like rotten eggs. When hydrogen sulfide hits the atmosphere and mixes with oxygen and water, it forms sulfuric acid. Acid rain. So not only was it raining constantly, it was raining acid. The soils were becoming acidified. The oceans were becoming acidified. For species already under stress from the changing climate, this was just one more problem piled on top of everything else. Trees started producing amber like crazy during this period. We find massive amounts of amber in the geological record from the Carnian, way more than we'd normally expect. And that's actually a telltale sign of stress. When trees are in serious trouble, when they're damaged or under environmental pressure, they produce resin as a protective mechanism. It's like their emergency response system. So the fact that we're finding so much amber from this time period tells us that plant life was really struggling. The forests were under siege from the changing climate, the acid rain, the flooding. It was rough for everyone. But while some species were having the worst time of their lives, others were about to hit the jackpot. Because here's the thing about extinction events, they're not just about death, they're also about opportunity. When ecological niches get emptied out, when dominant species die off and leave gaps in the ecosystem, that creates space for other species to expand and diversify. It's like when a big company goes out of business and suddenly all these new startups rush in to fill the void. Nature abhors a vacuum, right? So while the desert-adapted species were struggling and dying off, species that were adapted to wetter, more humid environments were suddenly living in paradise. And this is where things get really exciting, because one group in particular was perfectly positioned to take advantage of this new world. You guessed it, dinosaurs. Now, before the Carnian pluvial episode, dinosaurs were basically nobodies. They existed, sure, but they were small, not particularly numerous, and definitely not dominant. They were competing with all sorts of other reptiles and early mammals, and honestly they weren't winning that competition. But dinosaurs had one advantage that was about to become incredibly important. Many early dinosaurs were adapted to warm, humid environments. They could handle the heat and the moisture that was now spreading across Pangaea. Let me tell you about Herrerasaurus. This is one of the oldest dinosaurs we know of, and this thing was no joke. 6 meters long, weighing over 300 kilograms, basically the size of a large crocodile but built more like a predator, all teeth and claws and muscle. Before the rain started, Herrerasaurus was living in what's now South America, in an area called the Ishigualasto Formation. This place was a volcanic floodplain covered in dense jungle. Hot, humid, wet. The kind of environment that Herrerasaurus was perfectly adapted for. When the rain started falling and kept falling, guess what happened? Herrerasaurus's ideal habitat started spreading. That warm, humid jungle environment that used to be confined to coastal regions and volcanic areas started pushing deeper and deeper into the interior of Pangaea. Everywhere the rain touched, the climate shifted. Deserts turned into wetlands. Wetlands turned into swamps. Swamps turned into jungles. And Herrerasaurus was like, yeah, this is my time. So these dinosaurs started expanding their range. They pushed into territories that had been inhospitable desert before, and when they got there, they found something incredible. Empty ecological niches. The herbivores that used to dominate these areas were dying off or struggling to adapt. The competition was gone. It was like Herrerasaurus walked into an all-you-can-eat buffet with no line. The species that had been holding dinosaurs back, keeping them confined to marginal environments, were suddenly no longer a problem. And Herrerasaurus wasn't alone. Other early dinosaurs were having the same experience. They were spreading out across Pangaea, finding new habitats, new food sources, new opportunities. And here's where it gets even more interesting. We have actual evidence of this takeover preserved in the rock record. In the Dolomites in what's now Italy, scientists have found fossilized footprints from this time period. Thousands of them, laid down over about 3 to 4 million years spanning the Carnian pluvial episode. And when you look at these footprints chronologically, you can watch the dinosaur takeover happen in real time. Before the CPE, dinosaur tracks are basically absent from the record. You've got footprints from all sorts of other creatures, but dinosaurs, barely there. They're making up maybe a few % of the tracks at most, but then the rain starts and the ratio begins to shift. More and more dinosaur tracks start showing up. By the end of the Carnian pluvial episode, dinosaurs are making up over 90% of the fossilized footprints. 90%. That's not just success, that's complete ecological dominance. We see the same pattern in other parts of Pangaea too. In what's now Central Europe and in the Ixigualasto Basin in Argentina, the fossil record shows the same story. Dinosaurs go from being minor players to running the show in just a few million years, and it all traces back to that rain, that million-year storm that terraformed the planet and gave dinosaurs their shot at the big time. But let's get back to what was happening to the landscape itself, because the geological changes during this period were just as dramatic as the biological ones. Remember, this rain wasn't just changing the climate, it was physically reshaping the surface of the planet. When you dump that much water onto a previously arid landscape, things start to move. All that rainwater had to go somewhere, right? It couldn't just sit there, so it started flowing, seeking the lowest ground, carving channels, creating rivers where none had existed before. And because the land had been dry for so long, the soil wasn't prepared for this. There wasn't much vegetation to hold everything in place. The water just rushed across the surface, picking up speed, gathering force, carving deep gouges into the landscape as it went. This wasn't gentle erosion we're talking about. This was violent, aggressive reshaping of the terrain. Flash floods were probably common. Massive deluges of water racing across the land, carrying everything with them. Rocks, soil, vegetation, anything that wasn't firmly anchored got swept away. And remember, this rain was acidic. So it wasn't just physically eroding the landscape through force and volume, it was chemically eroding it too. There are certain types of rock that are particularly vulnerable to acid, limestone and dolomite especially. These rocks are made of calcium carbonate, and when acid hits calcium carbonate it dissolves, not quickly but steadily. Drip by drip, year after year, century after century, the acidic rainwater would seep into small cracks and fissures in these rocks and just start eating away at them from the inside. Over time, these tiny cracks would widen into channels. The channels would widen into passages. The passages would widen into chambers. And before you know it, you've got elaborate cave systems being carved out of the bedrock. We can actually see evidence of this process in the geological record. In Britain, there are these Triassic caves that were formed during the Carnian, carved out of Carboniferous limestone by acidic water. Places like Titherington in Gloucestershire. These caves were literally created by the million-year rain, dissolved out of solid rock by slightly acidic water, working patiently for hundreds of thousands of years, and these caves became habitats in their own right. New ecological niches for species to exploit. Dark, stable environments protected from the weather outside. Some creatures probably moved into these caves seeking shelter from the endless rain. Over time, cave-adapted species would have started evolving, creatures specialized for life in darkness. It's just another example of how this event wasn't just destroying old habitats, it was creating new ones too. But the real action was happening at the end of all those rivers and streams. All that water flowing across the land had to end up somewhere, and that somewhere was the ocean. And it wasn't bringing just water. It was bringing everything it had picked up along the way. eroded rock particles, dissolved minerals, organic matter, all of it getting dumped into the coastal waters and continental shelves. The runoff from the entire interior of Pangaea was flowing into the seas, and it was changing the ocean chemistry in dramatic ways. Ocean species were hit particularly hard during the Carnian pluvial episode. Harder than land species in many cases. See, when you suddenly increase the amount of fresh water and sediment flowing into the ocean, you're messing with everything that marine life depends on. Salinity levels change, water clarity decreases, nutrient balances shift. And on top of all that, you've got the ocean absorbing all that extra carbon dioxide from the atmosphere, which makes the water more acidic. Certain groups of marine life just couldn't handle it. Conodonts, these little eel-like creatures with elaborate tooth structures, got hammered. Ammonoids, those beautiful spiral-shelled cephalopods that had been so successful for millions of years, took major losses. Crinoids, also called sea lilies, filter-feeding animals that lived attached to the seafloor, struggled as the water got murkier and more acidic. Green algae populations crashed. Reef-building organisms, which need specific water chemistry to construct their calcium carbonate structures, found themselves in serious trouble as ocean acidification ramped up. Large areas of the ocean became anoxic during this period. Anoxic means lacking oxygen, and that's basically a death sentence for most marine life. When you've got all this organic matter washing into the ocean from the land and decomposing, it consumes oxygen. Add in warmer water temperatures which can hold less dissolved oxygen to begin with, and you've got a recipe for dead zones spreading across the seafloor. Fish, crustaceans, mollusks, anything that needs to breathe basically had to get out or die. The fossil record shows clear evidence of these anoxic events, layers of black shale deposited during periods when the ocean floor was essentially lifeless. But again, while some groups were suffering, others were thriving. Dinoflagellates, single-celled organisms that are a major component of ocean plankton today, did really well during the Carnian. They're adaptable, they can handle changing conditions, and they benefited from all those nutrients washing into the ocean. So while the large, charismatic megafauna of the Carboniferous seas were declining, these tiny organisms were having a population boom. The ocean ecosystem was being rebuilt from the bottom up. Back on land, the transformation was just as thorough. The geography of Pangaea was being rewritten. New river systems were forming, creating natural highways for species to migrate along. Lakes were appearing in areas that had been desert before. Wetlands were spreading. The entire hydrological cycle of the continent was being restructured, and this had huge implications for how species could move and spread. Before the rain, the interior of Pangaea was this massive barrier. Desert conditions meant that species adapted to humid environments couldn't penetrate very far inland. They were confined to the coasts and a few favourable pockets. But as the rain continued and those humid conditions spread, suddenly species could travel much further into the continent than ever before. Migration routes opened up. Populations that had been isolated from each other for millions of years could suddenly interact again. Gene flow between populations increased. It was like someone had built a highway system across a previously impassable wilderness. For dinosaurs, this was huge. They could expand from their original habitats and colonize new territories without having to cross deadly deserts. And as they spread, they diversified. Different populations adapting to different local conditions, evolving into new species. The Carnian pluvial episode essentially gave dinosaurs a blank slate to work with, a planet-scale terrarium perfectly suited to their needs. And they took full advantage of it. The thing that really gets me about this whole event is just how long it lasted. Like, try to wrap your head around 1,000,000 years of rain. 1,000,000 years. That's not even comprehensible on a human timescale. The entire span of recorded human history is only about 5,000 years. Modern humans have only existed for maybe 300,000 years. But this rain kept falling for over 1,000,000 years straight. Generation after generation after generation of dinosaurs, living their entire lives, being born and dying, under rain that never stopped. It was just the normal state of the world for them, and it wasn't constant the whole time either. Scientists have identified 4 major pulses, 4 distinct periods where the rain intensified to absolutely biblical levels. Each one of these pulses left its mark in the geological record, layers of sediment that tell the story of massive flooding and erosion. You can literally see them in the rock if you know what you're looking for. Dark bands of sediment deposited during the wettest periods, separated by lighter bands from the slightly less intense periods in between. Each pulse probably lasted tens or hundreds of thousands of years. Just imagine that. A rainstorm that goes on for 100,000 years, then maybe eases up a little bit, not stops but just becomes less intense, and then ramps back up again for another 100,000 years. 4 times this happened. 4 separate mega monsoons that reshape the planet. The biblical flood story talks about rain that lasted 40 days and 40 nights, and supposedly remade the entire earth. This was like that times 1,000,000, literally. It makes Noah's flood look like a typical rainy Tuesday in London, and each pulse brought its own changes, its own opportunities and challenges for life. Species that adapted during the first pulse might find themselves struggling during the second as conditions shifted again. But the species that could roll with the changes, that could adapt quickly to new conditions, those were the ones that thrived. Dinosaurs turned out to be really good at this. They were adaptable, they could exploit different food sources, different habitats. They had this flexibility that a lot of other groups lacked. You know what's really cool? We can actually track the dinosaur takeover through those footprints I mentioned earlier. The ones in the Dolomites. See, footprints tell a different story than bones do. Bones tell you what died in a particular place, but footprints tell you what was alive and active. They tell you what was walking around, hunting, migrating, just going about their daily lives. And the footprint record from the Carnian is incredibly revealing. Before the rain started, you've got all these tracks from other reptiles, early mammal relatives, all kinds of creatures making their way across the landscape. Dinosaur tracks are rare. Maybe 1 in 20 or 1 in 50 tracks belongs to a dinosaur. They're there, but they're minor players. Then the first pulse of rain hits, and you start seeing more dinosaur tracks. Still not dominant, but increasing. The ratio starts shifting. By the second pulse, it's maybe 1 in 10 tracks. By the third pulse, 1 in 5. And by the end of the 4th pulse, after the rain has been falling for over 1,000,000 years, dinosaur tracks make up over 90% of the fossil footprints. 90%. Think about what that means. It means that if you were standing on that landscape at the end of the Carnian pluvial episode and you looked at the tracks in the mud, 9 out of 10 would belong to dinosaurs. Everything else had been pushed to the margins. Dinosaurs had won. They'd taken over. And this pattern shows up in multiple locations across what was Pangaea, not just the Dolomites, Argentina, Central Europe. Other sites all show the same trend. Dinosaurs rising from obscurity to complete dominance in the span of a few million years. And here's what really blows my mind about this. The Wrangelian eruption, the thing that caused all of this. It was enormous. We're talking about a large igneous province, a flood basalt eruption that released magma for over 1,000,000 years. The amount of lava that poured out was staggering. It created these massive rock formations that we can still see today, spread across Canada and Alaska. Layers of basalt kilometers thick in places. This wasn't a supervolcano, it was 100 times bigger than a supervolcano. Just absolutely incomprehensible amounts of molten rock forcing its way to the surface and spreading across the landscape. Under normal circumstances, an eruption like that should have been catastrophic. It should have been extinction event level. And it was. Kind of. 30% of ocean species died out, which is nothing to sneeze at. But the weird thing is that the overall biodiversity didn't really drop. In fact, by some measures it increased. This extinction event actually made life on Earth richer and more diverse, not less. How is that even possible? Well, it comes down to the size of the eruption and the specific circumstances. The Wrangellian event was big enough to cause major environmental changes, big enough to kill off species that couldn't adapt. But it wasn't so big that it killed everything. It wasn't like the Siberian Traps eruption that caused the Great Dying, where ocean temperatures rose to 40 degrees Celsius and over 90% of all species went extinct. The Wrangellian eruption was more moderate. It raised global temperatures by 3 to 4 degrees, which is significant but not apocalyptic. It changed the climate dramatically, but didn't make the planet uninhabitable. So what you got was this perfect storm, pun intended, of conditions that cleared out old, established species while creating opportunities for new ones. The old guard, the species that had dominated during the dry Pangea period, they couldn't handle the new wet world. But for species that were pre-adapted to humid conditions, species like early dinosaurs, it was paradise. The competition was gone, the habitat was expanding, food was plentiful. They exploded into this new world and filled every available niche. And it wasn't just dinosaurs. Other groups benefited too. Certain types of plants that preferred wetter conditions spread like crazy. Ferns had a field day. Conifers expanded their range. The composition of forests changed dramatically. Before the Carnian, you had these dry adapted plant communities. After, you had lush, wet forests more similar to what we'd recognize as a rainforest today. The entire character of terrestrial plant life shifted. Insects benefited too. More plants meant more food for herbivorous insects. More herbivorous insects meant more food for predatory insects. Dragonflies, which had been around since the Carboniferous, probably did really well. They love humid environments. They breed in water. With wetlands spreading everywhere, dragonfly habitat was expanding massively. Same with other aquatic and semi-aquatic insects. Beetles diversified. The insect world was being remade. And all of this diversification, all of this evolutionary experimentation, it was being driven by one single geological event. The Wrangellian eruption changed the climate, which changed the water cycle, which changed the landscape, which changed the available habitats, which changed which species could survive where, which drove evolution in new directions. It's this incredible cascade of cause and effect, this chain reaction that rippled through every level of the ecosystem. The aliens in our story, these hypothetical observers watching Earth's history unfold, they would have been able to see this whole process play out in real time from their ship. They would have watched the Wrangellian province light up as the eruption began. They would have detected the spike in atmospheric carbon dioxide. They would have seen the greenhouse effect kick in, the global temperature rise, the intensification of the water cycle. They would have watched clouds form and move inland, delivering rain to areas that had been dry for millions of years. They would have seen rivers appear where none existed before, forests spread across former deserts, species migrate into new territories, and they would have been able to track the biological changes too if their sensors were good enough. They could have watched populations rise and fall, seen species go extinct, watched new species emerge and spread. They would have witnessed one of the most dramatic turnover periods in Earth's history, a time when the planet's entire ecological structure was being reorganized. The old Pangaea, that arid supercontinent dominated by desert-adapted species, was dying. The new Pangaea, a humid, wet world perfect for dinosaurs, was being born. The weather forecasts on their ship would have been depressingly consistent. Day after day, week after week, year after year, the prediction would have been the same. Rain, heavy rain, more rain. The aliens probably got tired of hearing it after a while, but down on the surface life was adapting, species were evolving, ecosystems were reorganizing themselves, and dinosaurs were seizing their moment. Herrerasaurus and its relatives were expanding their range across the continent. They were moving into territories that had been closed to them before, finding new prey, establishing new populations. And as they spread, they began to diversify. Different populations adapting to different local conditions, evolving new traits, eventually splitting into new species. The dinosaur family tree was branching, growing more complex, developing the incredible diversity that would characterize the Mesozoic era. Other early dinosaurs were doing the same thing. Some were adapting to be better predators. Some were shifting toward herbivory, taking advantage of all those new plant resources. Some were getting bigger. Some were staying small and nimble. Some were developing new hunting strategies, new defensive mechanisms, new ways of interacting with their environment. The evolutionary explosion was underway, and it was being fueled by the opportunities created by the endless rain. The fossil record from this period is frustratingly incomplete in some ways. We'd love to have more specimens, more detailed information about exactly what was happening, where and when. But what we do have is enough to tell the story. We have those footprints showing the dinosaur takeover. We have the geological evidence of the rain and the environmental changes. We have the extinction patterns in the oceans. We have the fossils of early dinosaurs spreading across Pangaea. All the pieces fit together to paint this picture of a planet in transition, being remade by forces beyond anyone's control. And the thing is, this kind of event, a flood basalt eruption triggering massive climate change, it's happened multiple times in Earth's history. The pattern repeats. Big eruption, climate change, extinction event. It's like Earth's reset button. Once in a while, geological processes just decide to shake things up and see what happens. Usually it's devastating. Usually it leads to mass death and ecological collapse. But sometimes, just sometimes, the conditions are right for something different to happen. The Carnian pluvial episode is really a perfect example of how Earth's major systems are all interconnected. You've got three massive cycles all interacting with each other in this complex dance, and when you mess with one, the others respond. It's like a giant machine where every part affects every other part. You've got the geological cycle, which is all about plate tectonics and volcanic activity, and the movement of the Earth's crust. You've got the carbon cycle, which tracks how carbon moves between the atmosphere, the oceans, the land, and living things. And you've got the water cycle, which is all about precipitation and evaporation, and the movement of water around the planet. Normally these cycles operate on different timescales. The geological cycle is slow, measured in millions of years. The carbon cycle can be faster or slower depending on what's happening. The water cycle operates on timescales from days to years. But during the Carnian pluvial episode, all three of these cycles got linked together in this incredible feedback loop that transformed the planet. It starts with the geological cycle. The Wrangelian Large Igneous Province begins erupting. Hot plumes from deep in the earth push magma up through the crust. The magma contains dissolved carbon dioxide, and as it reaches the surface and the pressure drops, that carbon dioxide comes out of solution and gets released into the atmosphere. So right away you've got the geological cycle feeding into the carbon cycle. Volcanic carbon dioxide that's been locked in the mantle for millions or billions of years is suddenly being dumped into the atmosphere at a massive rate. But then it gets more complicated because the magma isn't just erupting anywhere. It's erupting through an area that has huge coal deposits. Coal is ancient plant matter that's been compressed and heated over millions of years. It's basically concentrated carbon from the Carboniferous period, locked away underground. And when you introduce 1600-degree lava to coal, well, the coal starts to burn. It ignites, and once it starts burning, it's really hard to stop because there's just so much of it. So now you've got two sources of carbon dioxide going into the atmosphere. The volcanic emissions themselves plus the burning coal beds. And coal doesn't burn clean. It releases all sorts of stuff. Carbon dioxide, yes, but also carbon monoxide, sulfur dioxide, nitrogen oxides, particulates, ash, all kinds of nasty stuff. And hydrogen sulfide too, that rotten egg-smelling gas that reacts with oxygen and water to form sulfuric acid. All of this enters the atmosphere and starts affecting the carbon cycle in a major way. The atmospheric concentration of carbon dioxide climbs past 1,000 parts per million. To put that in perspective, pre-industrial levels were around 280 parts per million. Today, with all our cars and factories and power plants, we're around 420 parts per million, and that's enough to cause significant climate change. But during the Carnian, it hit over 1,000. That's massive. That's enough to drive serious greenhouse warming, and this is where the water cycle gets involved. Greenhouse gases trap heat from the sun. The energy that would normally radiate back into space gets trapped in the lower atmosphere instead. Temperatures rise, and when temperatures rise, evaporation increases. Warmer air can hold more water vapor, so more water evaporates from the oceans and lakes and rivers. That water vapor rises into the atmosphere, and water vapor is itself a greenhouse gas, so it traps even more heat. You've got a positive feedback loop going where warming causes more evaporation, which causes more warming. The energy trapped by all these greenhouse gases has to go somewhere. It can't just disappear, that would violate thermodynamics, so it goes into the Earth's systems. And the system best suited to absorb and move that energy around is the water cycle. The water cycle becomes supercharged. It speeds up. Water evaporates faster. Clouds form more readily. Precipitation increases. The whole cycle that normally might take weeks or months to complete starts cycling faster and faster. And here's where it gets really interesting. Clouds aren't just water vapor. They need something to form around, what scientists call condensation nuclei. Usually that's dust particles or salt crystals or other tiny particles floating in the atmosphere. Well, remember all those particulates being released by the volcanic eruption and the burning coal? Perfect condensation nuclei. So you've got more water vapor in the atmosphere than usual, more energy to drive cloud formation, and more particles for the water to condense onto. It's a recipe for massive cloud formation. These clouds get pushed inland by wind patterns. Normally, moisture-laden air from the oceans doesn't make it very far into the interior of a large continent before it loses its water. The clouds form, it rains along the coast, and by the time the air mass reaches the interior, it's been wrung dry. But with so much extra water in the atmosphere and so much extra energy in the system, these clouds can travel much further before they dump their moisture. They're being recharged continuously, picking up more water as they go. So rain that would normally only fall near the coast starts falling deeper and deeper into the continent. Pangaea's interior starts getting rain for the first time in millions of years. And it's not just a little rain, it's torrential. These aren't gentle showers, these are deluges. Monsoon-level rainfall, but sustained for ridiculous lengths of time. The ground, which has been dry for ages, can't absorb water that fast. The soil is compacted, there's not much vegetation to help with infiltration, so the water just runs off, forming streams, rivers, flash floods. It carves channels into the landscape, picks up sediment, carries it away. And remember, this isn't pure water. It's acidified by all that sulfur dioxide and hydrogen sulfide in the atmosphere. The rain is carrying sulfuric acid, not concentrated acid. It's diluted, but it's still acidic enough to affect things. When this acid rain hits limestone or dolomite rock, it reacts with the calcium carbonate. The rock literally dissolves, slowly but steadily. Tiny cracks widen into fissures. Fissures widen into channels. Over thousands of years, elaborate cave systems form. You can find evidence of this process all over the world today. In Britain, there are these Triassic caves carved out of Carboniferous limestone during the Carnian. Titherington in Gloucestershire is a great example. The cave system there was formed by acidic water, slowly dissolving the limestone over hundreds of thousands of years. You can see the geological layers, you can date when they formed, and it all points back to the Carnian pluvial episode. These caves weren't there before the rain started, and they wouldn't have formed without the specific conditions created by the Wrangelian eruption. And these caves became ecosystems in their own right, new habitats for life to colonize. Cave-adapted species started evolving, creatures that could live in permanent darkness, that could navigate by sound or touch instead of sight. It's another example of how this event wasn't just destroying old habitats but creating entirely new ones. The planet's biodiversity wasn't decreasing during the Carnian, it was being reorganized and in many ways increased. The effect on ocean chemistry was particularly dramatic. All that runoff from the land had to go somewhere, and it ended up in the oceans. Freshwater carrying dissolved minerals, eroded rock particles, organic matter, all flowing into the coastal seas. The salinity of coastal waters decreased as all this fresh water poured in. The water became murkier as sediment was suspended in it. Nutrient levels spiked from all the organic matter washing in. For marine life that had evolved in clear, stable, salty water, this was catastrophic. Coral reefs need specific conditions to thrive. They need clear water so sunlight can reach the symbiotic algae living in their tissues. They need stable salinity. They need specific water chemistry to build their calcium carbonate skeletons. When all those conditions change at once, corals die. And that's exactly what we see in the fossil record. Reef-building organisms took a major hit during the Carnian. But it wasn't just the reefs. Large areas of the ocean floor became anoxic. Oxygen levels dropped to zero in some regions. This happens when you have too much organic matter decomposing in the water. Decomposition uses oxygen, and if you have more organic matter than usual washing in from the land, plus warmer water temperatures which reduce how much oxygen water can hold, you get dead zones. Areas where nothing that needs to breathe can survive. These anoxic zones probably spread across significant portions of the ocean floor, especially in semi-enclosed seas and continental shelves. The deep ocean might have been okay. There's always some circulation bringing oxygen down from the surface. But the shallow seas, The areas where most marine life lived, those got hammered. You can see it in the rock record. Black shales deposited during the Carnian, indicating oxygen-poor conditions. Fossil assemblages showing major die-offs. Conodonts, ammonoids, crinoids, green algae. All these groups that had been doing fine for millions of years suddenly faced extinction. Not complete extinction. Some lineages survived, but major population crashes and loss of diversity. It was rough times if you were a marine organism during the Carnian. The pH of the ocean shifted too. When carbon dioxide dissolves in water, it forms carbonic acid. With atmospheric carbon dioxide levels over 1,000 parts per million, a lot of that CO2 was being absorbed by the oceans. The more CO2 that dissolves, the more acidic the water becomes. Ocean acidification. It's the same problem we're facing today with modern climate change, but turned up to 11. Ocean acidification is particularly bad for anything that builds a shell or skeleton out of calcium carbonate. Mollusks, corals, some types of plankton, even some fish. When the water becomes more acidic, it becomes harder to extract the calcium carbonate needed to build these structures. Existing shells can even start to dissolve. It's like trying to build a sand castle while someone's hosing it down. You're fighting against chemistry itself. So you've got all these interconnected effects cascading through the ocean ecosystem. Freshwater influx changing salinity, sediment making the water murky, nutrient overloading causing algae blooms and oxygen depletion. Temperature increases from greenhouse warming, ocean acidification making it harder to build shells. It's not one problem, it's a whole suite of problems hitting at once. No wonder 30% of marine species went extinct. But again, while some groups were suffering, others were thriving. Dinoflagellates, single-celled organisms that are major components of plankton today, did really well. They're adaptable, they can handle variable conditions, and they benefited from all those nutrients washing into the ocean. As other groups declined, dinoflagellates expanded to fill the available niches. The base of the marine food web was being restructured. On land, the transformation was just as thorough. The hydrology of Pangaea was completely rewritten. Before the Carnian, the interior was mostly endorheic basins. That means the drainage didn't reach the ocean. Any water that did manage to fall would collect in closed depressions, form temporary lakes that would evaporate, leaving salt flats behind. But with this much rain falling continuously, those basins filled up and overflowed. New river systems formed, cutting across the landscape, creating drainage networks that connected the interior to the coasts for the first time in millions of years. These new rivers became highways for species migration. Animals could follow them inland, moving into territories that had been inaccessible before. Plants could disperse their seeds along riverbanks, colonizing new areas. The connectivity of the continent increased dramatically. Populations that had been isolated from each other could interact again. Gene flow increased. Evolution accelerated. You know what's almost as interesting as how the rain started? How it ended. Because after over 1 million years of continuous precipitation, after 4 major pulses of mega monsoon activity, after completely reshaping the planet's ecosystems and geography, the rain finally stopped. Well, not stopped exactly, but it went back to normal patterns. The endless deluge gave way to regular weather. And the question is, why? What changed? It comes down to the Wrangelian eruption running out of steam. Remember, these flood basalt events are driven by hot plumes rising from deep in the Earth's mantle. They're not infinite. Eventually the plume weakens, or it shifts position, or the crust moves away from it. The magma stops flowing at the same rate. The eruption slows down, and when the eruption slows, so does the emission of volcanic gases. Less magma reaching the surface means less carbon dioxide being released directly from the mantle. And if the magma isn't reaching those coal beds anymore, they stop burning too. Or they burn themselves out after consuming all the easily accessible coal. Either way, the rate of greenhouse gas emissions starts to decline. It's not a sudden switch, it's gradual. The eruption probably sputtered along for a while, having active periods and quiet periods. But overall, the trend was downward. And once the emissions start declining, the carbon cycle starts working in reverse. Plants, which had been thriving in this warm, wet environment, they're pulling carbon dioxide out of the atmosphere through photosynthesis. They're building it into their tissues, their leaves, their wood, and when they die and get buried, that carbon gets locked away. Over time, some of it turns into coal, ironically enough. The same coal that would eventually get burned by another eruption, or by humans millions of years in the future. The carbon cycle continues. But in the short term, or what passes for short term in geological time, the plants are acting as a carbon sink. They're removing CO2 from the atmosphere faster than it's being added. Atmospheric carbon dioxide levels start to drop. The greenhouse effect weakens. Temperatures begin to decline back toward previous norms, and as temperatures drop, the water cycle slows down, less evaporation, less atmospheric moisture, less rain. The mega monsoons taper off. The fifth pulse of rain that you might expect based on the pattern of the previous four, it never comes. The system is winding down. The Wrangellian eruption has run its course. The planet is reaching a new equilibrium, but it's not the same equilibrium as before. Too much has changed. The landscape has been physically reshaped. Species have gone extinct. New species have evolved and spread. Ecosystems have been reorganized. You can't just go back to how things were. The dinosaurs, having expanded across Pangaea during the wet period, they're not going to just disappear because the climate is drying out again. They've established themselves. They've diversified. They've adapted to a wide range of environments. Some species might struggle as wetlands dry up, but others will adapt to the new conditions. And critically, they've already outcompeted most of their rivals. The species that might have kept dinosaurs in check before the Carnian, many of them are gone. The dinosaurs have the dominant position now, and they're not giving it up. This is what I mean when I say the Carnian pluvial episode was more of a reinvention event than a pure extinction event. Yes, species died. Yes, there was loss of biodiversity in some groups, but the net effect was a reshuffling and in many ways an enrichment of life on Earth. The old order was swept away, and a new order took its place. An order that would dominate for the next 150 million years. Think about that. 150 million years. That's how long the age of dinosaurs would last after the Carnian. From the end of the rain until the asteroid impact that would eventually wipe them out, dinosaurs ruled the Earth. And it all traces back to this one event, this one geological accident that gave them their opportunity. If the Wrangellian eruption had been bigger, it might have killed everything, including the dinosaurs. If it had been smaller, it might not have caused enough disruption for dinosaurs to gain their advantage. But it was just the right size to create chaos without causing total annihilation. The butterfly effect is a concept from chaos theory that says small changes in initial conditions can lead to vastly different outcomes. A butterfly flaps its wings in Brazil, and you get a tornado in Texas. It's about how tiny perturbations can cascade through complex systems and produce disproportionate results. Well, the Carnian pluvial episode is like the butterfly effect on steroids. except instead of a butterfly, you've got an eruption 100 times larger than a supervolcano. Instead of a tornado, you get the complete terraforming of an entire planet. The initial conditions were changed in a massive way, and the outcome was the rise of the dinosaurs and the reshaping of life on Earth. It makes you think about contingency in evolution, doesn't it? How much of history is determined by random chance. If that particular mantle plume hadn't punched through the crust in that particular location at that particular time, would dinosaurs have ever become dominant? Would mammals have had their chance earlier? Would Earth's history have been completely different? We can't know for sure, but it seems likely. The Carnian pluvial episode was a pivot point, a moment where the trajectory of life on Earth changed dramatically. And here's the thing that really keeps me up at night. Events like this have happened multiple times throughout Earth's history, and they'll happen again. The planet isn't done with us yet. We've had dozens of large igneous provinces formed over the past billion years. Each one represents a period of massive volcanic activity, climate change, and potential extinction. The Siberian traps caused the Great Dying. The Deccan traps might have contributed to the dinosaur extinction, along with the asteroid impact. The Central Atlantic magmatic province marked the Triassic-Jurassic boundary. The list goes on. These events are part of Earth's natural cycle. The planet isn't static, it's dynamic. It's constantly changing, constantly being reshaped by geological processes we can barely comprehend. Continents drift, mountains rise and erode, oceans open and close, and every once in a while, a hot plume from the mantle finds a weak spot in the crust and all hell breaks loose. It's happened before and it will happen again. The only question is when. The good news, if you can call it that, is that these events operate on timescales much longer than human civilization. The gap between major flood basalt eruptions is usually millions of years. The Wrangelian eruption happened 230 million years ago. The Deccan traps were 66 million years ago. We're probably safe for a while yet. Probably. But it does put our current environmental situation in perspective, doesn't it? We're worried about climate change from burning fossil fuels, and we absolutely should be. The changes we're causing are rapid and potentially catastrophic for modern ecosystems and human civilization. But compared to what the Wrangelian eruption did, our impact is minor. We've raised CO2 levels from 280 to 420 parts per million. The Carnian pushed levels past 1,000. We've raised global temperatures by about 1 degree Celsius so far. The Carnian raised them by 3 to 4 degrees. I'm not saying this to minimize the importance of climate change. What we're doing now is absolutely a problem, and we need to deal with it. But it does give you a sense of scale. Earth has survived far worse than anything humans can throw at it. Life has persisted through apocalyptic events that make anything in human history look trivial. The planet will be fine. It's us we should be worried about, us and all the other species currently living. Earth will adapt and move on with or without us. The fossil record is full of these cautionary tales, species that dominated for millions of years that seemed invincible, gone in a geological instant. The dinosaurs themselves, after ruling for 150 million years, wiped out by a combination of volcanic activity and an asteroid impact. The dominant species before them, gone in the Great Dying. No group's dominance lasts forever. Everything is temporary on geological timescales. But let's get back to the Carnian and its aftermath. After the rain stopped and the climate stabilized, the world that emerged was fundamentally different from the one that existed before. The geography had changed. New mountain ranges had been eroded, new river valleys carved, new caves hollowed out. The coastlines had shifted as erosion redistributed sediment and sea levels fluctuated. Pangaea was still one supercontinent, but its character had been transformed. The ecosystems had changed even more dramatically. The dry, desert-adapted communities of the early Triassic were gone, replaced by humid forest ecosystems. The species composition was completely different. Dinosaurs were everywhere, occupying ecological niches that had belonged to other groups before. New types of plants dominated the landscape. Ferns and conifers spread across regions that had been barren. The insect communities had been restructured. The marine ecosystems had been reorganized. And evolution wasn't done. The Carnian had set the stage, but the show was just getting started. Dinosaurs would continue to diversify throughout the rest of the Triassic and into the Jurassic and Cretaceous periods. They'd evolve into an incredible variety of forms. Tiny feathered dinosaurs and enormous sauropods weighing tens of tons, armored dinosaurs and horned dinosaurs, flying dinosaurs that would eventually become birds. The dinosaur radiation was one of the most spectacular examples of adaptive radiation in Earth's history, and it all started with the opportunities created by the Carnian pluvial episode. Other groups were evolving too. Mammals, which had originated around the same time as dinosaurs, continued their own evolutionary journey. They stayed mostly small during the Mesozoic, living in the shadows of the dinosaurs, but they were diversifying and adapting and waiting for their chance. Crocodilians split off from the dinosaur line and went their own way, eventually becoming the successful predators we know today. Pterosaurs took to the skies. Marine reptiles like ichthyosaurs and plesiosaurs invaded the oceans. Life was branching in every direction. The Carnian pluvial episode had opened the door to all of this diversification. By clearing out old species and creating new habitats, it had released constraints that had been holding evolution back. Species had room to experiment, to try new strategies, to adapt to new conditions. The result was an explosion of biological innovation that would characterize the Mesozoic era. You know what's really fascinating when you step back and look at the bigger picture? The Carnian pluvial episode is this perfect demonstration of how Earth's major systems are all interconnected in ways we're only beginning to understand. You can't separate the geology from the climate from the biology. They're all part of one integrated system, and when you perturb one part, everything else responds. The Wrangelian eruption was a geological event, sure, but it drove changes in atmospheric chemistry through the carbon cycle. Those atmospheric changes drove climate change through the greenhouse effect and the water cycle. The climate change drove ecological changes through habitat transformation and species turnover, and those ecological changes fed back into the carbon cycle as new plant communities spread and sequestered carbon in different ways. It's this beautiful, complex web of interactions, and the Carnian lets us see all of it playing out. And here's what really gets me. We're seeing the same mechanisms at work today. Obviously not on the same scale, and obviously not from a volcanic eruption, but the fundamental processes are identical. We're pumping carbon dioxide into the atmosphere by burning fossil fuels, the same fossil fuels that were formed from plant matter buried during events like the Carnian. That CO2 is trapping heat through the greenhouse effect, same mechanism. The extra heat is supercharging the water cycle, leading to more extreme precipitation events and more severe droughts, same pattern. Ocean acidification is affecting marine life that builds calcium carbonate shells, same problem. The parallels are kind of eerie. The difference is the rate. The Wrangelian eruption released its carbon over 1 million years. We're releasing comparable amounts in just a couple of centuries. The system doesn't have time to adjust gradually. Species don't have time to adapt slowly. Ecosystems can't reorganize themselves over millions of years. Everything is happening faster than natural rates of change, and that's what makes it so dangerous for current life on Earth. But the Carnian also shows us that life is resilient. Even in the face of massive environmental upheaval, even with 30% of species going extinct, life found a way. New species evolved, ecosystems reorganized, biodiversity rebounded. It took time, sure, billions of years, but it happened. Earth has this remarkable ability to heal itself, to adapt to new conditions, to continue supporting life even after catastrophic events. The planet is tougher than we sometimes give it credit for. The question for us today is whether human civilization can adapt fast enough to the changes we're causing. Because the planet will be fine in the long run. Life will continue, evolution will carry on, new species will emerge to replace those that go extinct. But will we be around to see it? Will the ecosystems we depend on for food and resources survive intact? That's less certain. The Carnian teaches us another important lesson about extinction and evolution. Extinction isn't just about death, it's about opportunity. Every species that went extinct during the Carnian opened up an ecological niche for something else. The extinction of desert-adapted species created opportunities for humid environment specialists. The decline of old reptile lineages made room for dinosaurs. Death and birth are intertwined in the evolutionary process. You can't have one without the other. This might sound callous when we're talking about modern extinctions. We don't want to lose species, and we shouldn't be blasé about it. Every extinction represents the loss of millions of years of evolutionary history, genetic information that can never be recovered. But from a purely ecological perspective, extinctions do create opportunities for the surviving species to diversify and adapt. That's cold comfort when we're talking about losing elephants or rhinos or tigers, but it's the reality of how evolution works. The dinosaurs certainly took advantage of their opportunities. After their rise to dominance in the late Triassic, they continued to evolve and diversify throughout the Jurassic and Cretaceous. You had herbivores getting bigger and bigger, evolving into the massive sauropods that weighed as much as modern whales. You had predators getting more sophisticated, developing better senses, faster running speeds, more effective hunting strategies. You had some lineages developing armor, others developing horns, others developing elaborate display structures for mate competition, and some dinosaurs went in completely unexpected directions. There were tiny feathered dinosaurs living in trees, experimenting with gliding and eventually true flight. These would eventually give rise to birds, which are literally modern dinosaurs that never went extinct. Every time you see a pigeon or a crow or an eagle, you're looking at a living dinosaur. The lineage that started expanding during the Carnian pluvial episode never really ended. It just transformed. The Mesozoic era, the age of dinosaurs, lasted about 180 million years from the Triassic through the Jurassic and Cretaceous. To put that in perspective, modern humans have only existed for about 300,000 years. Homo sapiens is about 0.2% as old as the dinosaur era was long. If the age of dinosaurs was a 24-hour day, all of human history would be less than a minute. They were astoundingly successful by any measure, and it all goes back to that rain, that million-year storm that gave them their chance. Without the Carnian pluvial episode, dinosaurs might have remained minor players in Triassic ecosystems, eventually going extinct like so many other lineages. Instead, they seized the opportunity created by environmental catastrophe and rode it to 180 million years of dominance. They became the most successful large land animals in Earth's history. Of course, their reign eventually ended. About 66 million years ago, another extinction event struck. This time, it was a combination of factors. The Deccan Traps in India were erupting, creating similar conditions to the Wrangellian event: volcanic activity, climate change, environmental stress. But then an asteroid about 10 kilometers in diameter slammed into what's now the Yucatan Peninsula in Mexico. The combination was too much. The impact winter, the acid rain, the fires, the collapse of food chains, it was more than most large animals could survive. The dinosaurs, except for the bird lineages, went extinct. After 180 million years of success, they were gone in what was probably just a few thousand years. The dominant species of the Cretaceous wiped out. But again, their extinction created opportunities. With the dinosaurs gone, mammals could finally expand into the large animal niches. They'd been waiting in the wings for the entire Mesozoic, staying mostly small, mostly nocturnal, mostly trying not to get eaten by dinosaurs. But now the dinosaurs were gone, and the mammals exploded. The Paleogene and Neogene periods saw mammals diversify into an incredible array of forms: whales going back to the oceans, bats taking to the skies, horses, elephants, cats, dogs, bears, primates, all the groups we're familiar with today. They all evolved in the wake of the dinosaur extinction, and eventually one line of primates evolved larger brains, started making tools, developed language, built civilizations. Us. We're here because the dinosaurs went extinct. We're beneficiaries of that catastrophe the same way dinosaurs were beneficiaries of the Carnian. It's humbling when you think about it. Our entire existence as a species traces back through this chain of accidents and extinctions and environmental catastrophes. If the Wrangellian eruption hadn't happened, no dinosaur dominance. If the asteroid hadn't hit, no mammalian radiation. If any of 1,000 other events had played out differently, we wouldn't be here. The path from single-celled organisms to modern humans is littered with contingencies, random events that could have gone differently and changed everything. The Carnian pluvial episode is just one node in that vast network of causality, but it's a crucial one. It reshaped life on Earth in ways that echoed for hundreds of millions of years. The dinosaurs that rose to prominence during the Carnian would dominate ecosystems for the rest of the Mesozoic. The plant communities that spread during the wet period would form the basis for terrestrial ecosystems going forward. The geological features carved by the rain would persist for millions of years. Even the carbon that was released and then resequestered would eventually become the fossil fuels we're burning today. And that brings us full circle in a weird way. The coal that's contributing to modern climate change, some of it was formed from plants that grew during and after the Carnian pluvial episode. Plants that thrived in the humid conditions created by the Wrangellian eruption. They pulled carbon out of the atmosphere, stored it in their tissues, died and got buried, and over millions of years turned into coal. And now we're digging it up and burning it, releasing that ancient carbon back into the atmosphere, driving our own version of climate change. The carbon cycle continues, just with humans as the new actors. The geological record preserves all of this history if you know how to read it. Layers of rock laid down during the Carnian show the evidence of the environmental changes. Flood deposits from the intense precipitation, black shales from anoxic ocean conditions, cave systems carved by acidic water, fossil assemblages showing species turnover. It's all there. written in stone, waiting to be discovered and interpreted. Every layer tells a story about what conditions were like when it formed, what species were living, what the climate was doing. Scientists studying the Carnian have pieced together this remarkable story from fragmentary evidence scattered across the globe. A fossil here, a rock formation there, chemical signatures in ancient sediments. It all comes together to paint a picture of this pivotal moment in Earth's history. And we're still learning new things. New discoveries are made every year that refine our understanding of what happened during the Carnian and why it mattered. The story is still being written. One thing that's become clear is that the Carnian pluvial episode was a global event, not a regional one. We find evidence of the wet conditions in what's now Europe, North America, South America, Asia. The whole of Pangaea was affected, and the biological turnover happened globally too. It's not like dinosaurs took over in one region while other groups remained dominant elsewhere. No, the pattern is consistent worldwide. This was a planet-scale reorganization of ecosystems. That global nature makes it different from more localized environmental changes. Regional climate variations happen all the time, and they drive local adaptations and extinctions. But events that affect the entire planet simultaneously are rare, and they have outsized impacts on evolutionary history. The Carnian was one of those rare global events, and its effect shaped the trajectory of life for the next 150 million years. So let's come back to where we started, and really think about what the Carnian pluvial episode means for us today. We've travelled through this incredible story of a million-year rainstorm, watched dinosaurs rise to dominance, seen the planet completely transformed by geological forces beyond anyone's control. But what's the takeaway? What can a 230 million-year-old extinction event teach us about the world we're living in right now? First off, it shows us just how interconnected everything on this planet really is. When that Wrangelian eruption started pumping out carbon dioxide and triggering the burning of coal beds, it set off a chain reaction that affected literally every ecosystem on Earth. The atmosphere changed, the climate changed, the water cycle changed, the oceans changed, the land surface changed, and all of these changes fed back into each other, creating cascading effects that rippled through the entire biosphere. Nothing exists in isolation. Everything is connected to everything else through these complex webs of cause and effect. And that's true today too. When we pump greenhouse gases into the atmosphere, we're not just warming the air, we're changing ocean chemistry through acidification. We're altering precipitation patterns and making extreme weather more common. We're shifting the ranges of species as they try to track their preferred climates. We're affecting crop yields and water availability and disease patterns. Every action has multiple consequences, many of them unintended and hard to predict. The Earth system is complicated, and when you perturb one part of it, you're affecting the whole thing, whether you meant to or not. The Carnian also teaches us about timescales and how important they are. The million-year reign sounds like an eternity to us because our lives are so short. But in geological terms, it's actually pretty brief. The changes it caused happened rapidly by Earth standards, and yet life adapted. Species evolved, ecosystems reorganized. But they had time to do it because even though the event was geologically brief, it still played out over hundreds of thousands of years. There was time for natural selection to work, for populations to shift their ranges, for new species to evolve and fill empty niches. Compare that to what's happening now. We're causing climate change at a rate that's orders of magnitude faster than what happened during the Carnian. We're compressing similar amounts of atmospheric change into centuries instead of hundreds of thousands of years. Evolution doesn't work that fast. Species can't adapt that quickly. Ecosystems can't reorganize on human timescales. That's why the current situation is so concerning. It's not that the changes we're causing are unprecedented in Earth's history. It's that they're happening so fast that natural systems can't keep up. But the Carnian also offers some hope in a weird way. It shows that life is resilient. Even in the face of massive environmental upheaval, even with significant extinctions, the biosphere bounced back. New species evolved to replace the old ones. Ecosystems found new equilibrium states. Biodiversity recovered. Earth has been through catastrophes before, and life has persisted. The planet knows how to heal itself, given enough time. The key phrase there is given enough time. On million-year timescales, Earth is incredibly resilient. On human timescales, not so much. The ecosystems we depend on for food, water, resources, they're adapted to relatively stable conditions. Rapid change is disruptive. So while we can take some comfort from life's long-term resilience, we shouldn't be complacent about short-term disruptions that could cause enormous human suffering. Another lesson from the Carnian is that extinction is natural and inevitable, but it's also irreversible. Every species that went extinct during that event is gone forever. Their genetic information, accumulated over millions of years of evolution, was erased. Now, new species eventually evolved to fill similar ecological roles, but they weren't the same. Evolution doesn't repeat itself exactly. Each species is unique, a product of its particular evolutionary history and circumstances. Once it's gone for good. We're currently living through what some scientists call the sixth mass extinction. Species are going extinct at rates far above the background norm, primarily due to human activities. Habitat destruction, pollution, climate change, overexploitation, invasive species. We're hammering biodiversity from multiple directions simultaneously. And just like during the Carnian, some species are going extinct while others are adapting and even thriving. Rats, crows, cockroaches, dandelions, these adaptable generalists are doing fine. It's the specialists, the species with narrow environmental requirements, that are struggling. The difference is that this time, one species, us, is causing the changes. We're not passive observers watching geological processes unfold. We're active participants, arguably the main driver of current environmental change. That gives us both responsibility and agency. We can choose to reduce our impact, to preserve habitats, to mitigate climate change, or we can choose not to. The planet doesn't care either way. It'll adapt and move on regardless. But we might care about what kind of world we're leaving for future generations. The Carnian also highlights something about Earth's natural variability that I think is important to remember. The planet is not stable. It never has been. The climate we think of as normal, the ecosystems we're familiar with, they're just temporary snapshots of a constantly changing system. On long enough timescales, everything changes. Continents drift, mountains rise and erode, sea levels fluctuate, climates shift. The Earth we see today is radically different from the Earth of the Triassic or the Carboniferous or any other period in the past, and it'll be different again in the future. That doesn't mean we should be cavalier about the changes we're causing. Just because change is natural doesn't mean all changes are equivalent or that the pace doesn't matter. But it does put things in perspective. We're not preserving some eternal natural state by protecting the environment. We're choosing which version of Earth we want to live on, which ecosystems we want to maintain, which species we want to coexist with. That's a value judgment, not a scientific one. Science can tell us what's changing and why and what the consequences might be. But deciding what to do about it is ultimately a human choice based on human values. Looking at the bigger arc of Earth's history, the Carnian pluvial episode is just one event in a long series of dramatic changes. The planet has been through far worse. The Great Dying killed 90% of species. The asteroid impact that killed the dinosaurs was probably more immediately catastrophic than anything the Carnian threw at life. The Snowball Earth episodes in the Proterozoic, when the entire planet froze over, those were arguably more extreme than anything in the Phanerozoic. Earth is no stranger to catastrophe, but each of these events shaped what came after. The Permian-Triassic extinction wiped the slate clean and allowed the Mesozoic fauna to emerge. The asteroid impact ended the age of dinosaurs and enabled the mammalian radiation. The Carnian gave dinosaurs their opportunity to become dominant. These weren't just disasters, they were evolutionary crucibles, periods of intense selection pressure that drove innovation and diversification. Without catastrophes, evolution might proceed much more slowly. Disruption, as terrible as it is for the species experiencing it, seems to be an engine of long-term diversity and complexity. That's not an argument for causing disruptions. We shouldn't go around wrecking ecosystems on purpose because it might lead to interesting evolution millions of years down the line. But it is a recognition that change and disruption are built into the system. They're features of how Earth works, not bugs. Life evolves in response to changing conditions. Extinction clears out old forms and makes room for new ones. The biosphere is dynamic, not static. The carbon cycle, which played such a central role in the Carnian story, continues to operate today. Carbon moves from the atmosphere to the oceans to living things to rocks and back again in this endless cycle. Volcanic activity releases carbon stored in the mantle. Photosynthesis pulls it out of the air. Respiration and decomposition release it back. Weathering of rocks consumes it. Burial of organic matter sequesters it. The burning of fossil fuels releases it. Carbon is constantly moving through Earth's systems, and the balance between sources and sinks determines atmospheric CO2 levels. Right now, we're adding carbon to the atmosphere faster than natural sinks can remove it, so levels are rising. Eventually, assuming we stop adding carbon, or at least slow down significantly, the system will reach a new equilibrium. Weathering will consume the excess CO2 over hundreds of thousands of years. Plant growth might increase in response to higher CO2 and warmer temperatures, pulling more carbon out of the air. The ocean will continue absorbing CO2, though at the cost of continued acidification. The carbon cycle will self-correct, but on geological timescales, not human ones. That's the thing about Earth systems. They have tremendous inertia. They respond slowly to perturbations, but once they start moving in a new direction, they're hard to stop. We're pushing the climate system into a new state, and even if we stopped all emissions tomorrow, it would take decades or centuries for the system to stabilize at a new equilibrium, and then it would take tens of thousands of years to return to pre-industrial conditions naturally. We've set things in motion that we can't easily reverse. The Wrangelian eruption did the same thing. Once it started, there was no stopping it. The magma had to work its way through the crust until the driving force weakened. The coal had to burn until it ran out or conditions changed. The rain had to fall until the water cycle slowed down. It was an inevitable consequence of the geological processes involved. You can't just turn off a flood basalt eruption. You have to wait for it to run its course. In a similar way, we can't just instantly reverse the climate change we've set in motion. We can stop making it worse by reducing emissions. We can adapt to the changes that are now inevitable. We might even be able to actively remove carbon from the atmosphere through various technological means, though that's difficult and expensive. But we can't snap our fingers and go back to the way things were. The system has momentum. So what does all this mean for our hypothetical time-travelling aliens, the ones who witnessed the Carnian pluvial episode and watched dinosaurs take over the world? What would they think if they came back today and saw what we're doing? Would they see parallels between the Wrangelian eruption and our industrial civilization? Would they recognize the patterns of climate change and ecosystem disruption? I think they would. The mechanisms are the same, even if the details differ. Greenhouse gas emissions driving climate change affecting the water cycle, ecosystem disruption leading to extinctions and turnovers. It's the same fundamental story playing out again with different actors. The Carnian had volcanic eruptions and burning coal beds. We have power plants and automobiles. The Carnian played out over 1 million years. We're compressing similar changes into centuries, but the underlying dynamics are identical. And maybe those aliens would see something else too. Maybe they'd recognize that we're at a choice point, a moment where our decisions will shape the trajectory of life on Earth for millions of years to come. Just as the Carnian set the stage for the age of dinosaurs, what we do in the next few decades will determine what kind of planet our descendants inherit. Will we stabilize the climate and preserve biodiversity? Will we adapt to a hotter, more chaotic world? Will we trigger cascading collapses that reduce Earth's complexity? The aliens don't know yet because the outcome isn't determined. It depends on choices we haven't made yet. The Carnian pluvial episode reminds us that Earth is a dynamic, changing planet where catastrophes and opportunities are two sides of the same coin. It shows us that life is resilient over long timescales, but vulnerable over short ones. It demonstrates that all of Earth's systems are interconnected and that changes in one area ripple through everything else. And it teaches us that the history of life is shaped by chance and contingency, as much as by deterministic processes. 230 million years ago, a geological accident gave dinosaurs their shot at dominance. They took that opportunity and ran with it, becoming the most successful large land animals in Earth's history. 180 million years later, another accident ended their reign and gave mammals their chance. And here we are, the descendants of those opportunistic mammals, now shaping the planet ourselves. We're the latest chapter in this ongoing story of change and adaptation and extinction and evolution. The rain that fell for 1 million years changed everything. It reshaped the land, reorganized ecosystems, set the stage for an entire era of Earth's history. And in doing so, it reminds us that change is the only constant on this planet. Earth was different in the past, it's different now, and it'll be different in the future. The question isn't whether things will change, they definitely will. The question is how we'll respond to the changes we're experiencing and causing. Will we adapt? Will we mitigate? Will we simply react as things unfold? Those are the questions facing us today, the same questions every species has faced when confronted with environmental upheaval. The aliens in our story left after witnessing the dinosaur takeover, having seen one of the great transformations in Earth's history. But the story didn't end there. It continued for another 230 million years, through the Mesozoic, through the mammalian radiation, through the rise of humans, and it continues today, with us playing a starring role we never auditioned for. We're not just watching Earth